Here we go with section 9. So we start out by looking a little more carefully at work and kinetic energy, something I rather incompletely and superficially mentioned right at the end of section 7. Let's start out with work. Now, from I think it was section 5, work is the dot product of the force and the displacement. Let's apply that to a rotating object. So we have here some generic thing that's rotating about this point right here. This could be a very badly drawn door rotating around its hinges. It could be a very badly drawn fan spinning around its center here. Well, it wouldn't be a fan because nobody'd have a piece of string attached to the fan probably, but whatever it is, here's the axis of rotation. The axis passes through the page here at this point. And at this point up here, there's a force acting. Maybe there's a string attached at that point and somebody's pulling it. And we're going to consider a very small displacement. The point where the force acts starts out here, and a very short time later, that point where the string is attached has moved over to here instead. So it's moved through a distance ds, and this force, I'm going to write all this down for you in a moment, but this force, which is doing the work, makes an angle of 90 minus phi with the displacement vector ds. Phi here, the Greek letter phi, is the angle between the radius out to that point where the force acts. The angle between that radius and the force vector is phi. The angle between the force and the displacement of the point where the force acts would be 90 minus phi. That's the angle we need in the definition of work. Remember, force times displacement times the cosine of the angle in between. This one is the angle in between. So, writing out the details. I guess I should have had that a little higher. Higher, a little bigger. Makes the lighting better. Okay. So in that picture I was just pointing at, picture on the handout. The work done by that force, dW, it's just an infinitesimal amount of work because we only moved the object an infinitesimal amount. Just a moment, I may need to, nope, I may get interrupted here in a while, but that was not it. Anyhow, force times displacement, using the definition of the dot product. Force times the displacement times the cosine of the angle between them. Well, here's why they made you learn trig identities. Cosine of 90, of course this is 90 degrees, pi over 2 radians if you'd rather look at it that way. Cosine of 90 minus phi for any angle phi would be equal to the sine of that angle. Substitution. Remember, this was, I think, section 7. If you've got, I think I was talking about a bicycle wheel then and said that if you've got a point on the edge of the wheel that travels a distance s, the angle in radians is related to the distance moved, this arc length here, s, is related to theta in radians by s equals r theta. Well, that's what I've used here, except instead of having turned some macroscopic amount like 30 degrees or something, we're saying that the angle and the distance are infinitesimal. Okay, you're taking the limit here where these things approach 0, so it becomes ds and d theta, but this is the substitution that I'm using here. And remember, since this is the equation that defines what a radian is in the first place, you have to use radians for this to be true. If you, for example, use revolutions, you're off by a factor of 2 pi. So this substitution is only valid if you measure in radians, and therefore whatever I end up with will require that you use radians. Let's just rearrange where the parentheses are. Rearrange the order. I've written a few things too. The radius times the force times the sine of the angle in between them. That's the torque produced by that force. So, just as when you're talking about translational motion, work is basically the force times the distance. Well, that becomes rather awkward when you're talking about something that's rotating, because a point that's farther from the pivot travels a greater distance than a point that's closer to it. The distance varies all over a rotating object. Much more convenient to think in terms of torques and angles when you're dealing with rotation. So for translational motion, work is force times distance. Here it's the torque times the angle. Again, how hard are you pulling times how far did you pull? How hard are you twisting times how far did you twist it? Well, this is just for an infinitesimal amount of motion. If this object is going to turn some finite amount, 75 degrees or whatever, then in the most general case, where either the size of the force or the angle might vary as you move along, you would have to use that to calculate the work done in each little piece of the motion of the thing, and add up the work done in all those little increments to get the total. So the total work I'm going to label things carefully here because I don't want anybody to mix up W for work with omega for angular velocity. In general, the integral of the torque times d theta would give you the work done by a torque if everything stays constant. the magnitude of the force remains constant. The angle, the angles don't change as it moves along. In that case, if the torque is a constant, you can take it out in front of the integral. You're left with just the integral of d theta, which gives you theta. So work equals tau times theta. Everything stays constant, which, again, I've said to you before, I'm not going to expect you to know how to integrate until you get back after the Christmas break. So this will be the only thing you really need to worry about. I guess that should be in there, shouldn't it? So that's work. And then back in at the very end of section 7, I just kind of asserted that the kinetic energy is equal to 1/2 I omega squared. I've got a little more time here in this unit to give you some justification for that. Everybody's sitting out there going, oh, no, we believe you. You don't have to. Well, it's only take a couple minutes. So work energy theorem. The work done on an object equals the change in its kinetic energy. If that rotating object on the handout there, if it moves just a little bit, the work is the torque times the angle. We saw, I think it was in section 7, that torque is equal to the moment of inertia times the angular acceleration. That's the rotational counterpart to F equals ma, tau equals I times alpha. This is also a relationship that's only valid if you use radians. So if it wasn't enough that this is only true when you use radians, this kind of makes it doubly required that you have to be measuring in radians with what we're going to come up with here. The definition of angular acceleration was actually, I want that just, oh no, that's too low, but anyhow, alpha by definition is the derivative of omega with respect to time. And I'm just going to kind of slide the dt over so it's underneath the d theta instead of under the d omega. This, by the way, is omega for angular velocity, not to be confused with W for work. This looks like an algebraic thing I've done here, but actually it's the chain rule. Maybe I don't need to get too nitpicky about the math here. The important thing, I guess, from the physicist's point of view is it works, but it's actual. This is not division. Maybe I should emphasize that. This is not d omega divided by dt. It's actually the derivative of omega with respect to time. And you can show using the chain rule that this would be equivalent to, but It sure looks like you just slid that over so it's underneath there. And if you want to think of it that way, you're going to get away with it. I was just dwelling on technicalities is all. So d omega with respect to time is the definition of angular velocity. So the work, pointy on the bottom when it's W, rounded on the bottom when it's omega. So I recopied the I recopied the d omega, and d theta over dt is omega. So I've got that. And now if you want to know how much work is done with some finite rotation, instead of some tiny amount of movement where you're doing the limit as it approaches zero, if you're going to, let the thing turn 3/4 of a turn or something like that, you'd have to integrate. You have to add up the work done in each small increment. W is the integral of dW And for those of you in Calc 1, which is probably the majority of the class, well, this will make sense before very long. You haven't probably gotten to integration and calculus yet, but just look back at it in a month or two and it'll be very straightforward. Moment of inertia is a constant. An integral is just an antiderivative, okay? It's just differentiation done backwards. So just like when you take a derivative, constants just sit around and do nothing. You just recopy them onto the next line. So moment of inertia is a constant, and you can, because it's a constant, you can write it out in front of the integral. These are the limits of integration. An integral is a summation. You're adding up the work done in each of these small increments. You begin summing when omega equals this value, omega initial, and at the end of where you're summing everything up, it reaches a value omega final. The way you integrate is it's just derivatives done backwards, okay? The derivative of 1/2 omega, actually, technically, it's a differential, not a derivative, but the derivative of 1/2 omega squared would be omega to the first power. So that makes the integral of omega to the first power 1/2 omega squared. And then you have to evaluate it at the upper and lower limits of integration. So this shows that the work done as this, oh, I think that's my cart coming up the hall. I'm going to pause it here. Okay, I'm back. So work equals the change in kinetic energy. Work equals the change in the quantity 1/2 I omega squared. Therefore, 1/2 I omega squared equals kinetic energy, rotational kinetic energy to be precise. So I left my chalk over here. So Little r subscript there is for rotational. And this is yet another relationship where it's required you have to use radians. When in doubt, convert to radians. Not always necessary, but never wrong. Okay, so here's where I should point the camera back at the handout. Probably raise it up a little bit. Example number 1, right there, is actually one that I did before. You've got a disc mounted on some sort of frictionless vertical axle, and there's been a cord wound around it several times, and you're pulling on that, which creates a torque that makes the thing spin faster and faster. It starts from rest. How fast is it spinning around after 10 revolutions? This should sound kind of familiar because this is a rerun, okay? We've already done this example at the end of section 7, or somewhere in section 7. It wasn't the last one. The way I did it there is I used torque equals I times alpha to find the angular acceleration, and then step 2, from the angular acceleration, I got the thing the question was actually asking for, the final angular velocity. I'm going to just run through it again using energy methods this time, which actually I think is a little more straightforward because it's one step, and here's the answer, instead of, first step, solve for alpha, step 2, take alpha and get omega. Taking an energy approach, you just set up one equation, and the answer drops out of that one equation without having to go on to a second one. So it looks like this. Another form of the work energy theorem, one that includes potential energy. This time the W is just the work done by non-conservative forces, whereas back over here, this was the total work done by any force at all. But anyhow, this should look kind of familiar from a few weeks ago. The initial energy, well, first of all, potential energy doesn't enter into this because this wheel just stays in one spot and spins around. It doesn't get higher or lower. There's no change in potential energy. The E's are just going to be kinetic energy in this case. And it starts out with none of that because it's at rest. The work, like it says over there, torque times the angle. So you start out with no energy. Some work is done by the torque from the string, which gives it some kinetic energy in the end. Kinetic energy is 1/2 I omega squared. Well, we have several things to figure out before we can drop the numbers in there in no particular order. The moment of inertia of that disk. Moment of inertia, you have to look back into that collection of formulas that was back in section 7 on the formula sheet. It says there that a disk is 1/2 mr squared. And the mass and the radius are both given in the question. The radius is 0.2 of a meter. The mass is 5 kilograms. And just like when I used the same formula when I did this example before, you put in the two numbers I just mentioned, and the inertia comes out equal to 0.1 theta. This is one of those places where you have to have radians. So can't put in 10 revolutions. You have to call it 20 pi radians. And the torque. I'm sure I've mentioned before that an ongoing problem is people mixing up torque with force. If this was a test question, I am sure there would be probably more than one paper where people just stuck in the 15 newtons. Torque is newtons times meters. Force times how much leverage does that force get? Force acts at the outside edge of the disk, 0.2 of a meter from the axis of rotation. So 3 Newton meters for the torque. Putting it all together, for tau we have 3, for theta 20 pi, then you get to the equal sign, moment of inertia is 0.1, and at this point the battle is pretty much won. All that's left is a little bit of elementary algebra. So to solve, wait a minute, that looks better. To solve for omega, you divide both sides by the 1/2, you divide both sides by the 0.1, take the square root of the whole mess, punch it up. And what do you know? I got the same answer I got doing it the other way. Well, let's go back over here and see what's next. A lot of fuzzy writing is what's next. No, didn't work that time. Gotta try again. It's pretty sharp on that piece of paper. Now, wait a minute. Didn't really plan on spending the whole afternoon trying to make this focus. Make it a little closer, a little farther away. Okay, one more time, and then I'm just going to live with it, fuzzy or not, because I can read you what it's. Okay, that's Oh, seriously? Well, anyhow. Technology. Well, what this says, if you can't quite make it out, is it says an object moving from place to place and rotating at the same time. Okay? Near the beginning of the course, we had something like a box sliding down a ramp where you have purely translational motion. Now, more recently, we've had purely rotational motion. This thing spins around, but the center of the object stays right there. What if you have both things going on at once? Like, well, in this next example, there's, oh, now you focus. Oh. You got a ball rolling down a ramp. Instead of a box sliding down the ramp, you've got a ball rolling down the ramp. Or, you've got a wheel on a car as it rolls down the road or something like that. Well, if you have something which is going through rotational and translational motion at the same time, the total kinetic energy is the two things added together. Okay, you've got the translational kinetic energy of its center of mass. If the ball at some particular instant is moving at 5 meters per second, you stick that would be the center of the ball. Okay, if the point that the ball is rotating around is moving at 5 meters per second, you stick that in 1/2 mv squared. And then if the ball at the same time is rotating around that point, the rotational energy is 1/2 I omega squared, and you add the two things together. Okay, if it's rotating and translating at the same time, you should just write that down for you, is what I ought to do. Let's see. Yep. So, translation and rotation at the same time. For example, a ball that's rolling across the floor, rolling down a ramp, whatever. The center of the ball is moving at the same time that the ball is spinning around its center. Its total kinetic energy (1/2 mv squared), where v here well, I guess I'm assuming here that the ball is rotating around its center of mass. V would be the velocity of the center of mass, plus omega here would be the angular velocity as it spins around. In other words, if you're running alongside the ball so that its center of mass is stationary relative to you, what angular velocity do you see it rotating with from that point of view? So omega around the center of mass. By the way, maybe I should have emphasized this a little more a few minutes ago. Hopefully everybody, back over here. Hopefully everybody caught on to the fact that this is W for work, and this is omega for angular velocity. Always kind of a sensitive issue. We'll put a big old box around that. And then we have an example. And I'm not going to put the camera back there and spend 10 minutes trying to make it focus again. If you want to read the example, back up, I think it was on camera a few minutes ago, or it probably will be again in a few minutes. But it just shows a picture of a ball at the top of a ramp. And on the picture, it's labeled that this is kind of a long, tall ramp, actually. It shows that the top of the ramp is 15 meters above the bottom of the ramp. The ball is a solid sphere. In other words, it's a bowling ball, not a basketball. Well, except the bowling ball's got those 3 holes in it, but it rolls without slipping. That's significant because that means that the speed, if it rolls without slipping, that means that the speed of the center of the ball relative to the ramp is the same as the speed of a point on the edge of the ball as it goes around the center. If it slips, those are 2 different speeds. No significant energy is lost. Now, you can't say it's frictionless. I chose my words carefully here. If the ramp was completely frictionless, you'd let go of the ball and it would slide down without rotating. But there is some static friction that makes it rotate, but we'll say that static friction does not dissipate any significant amount of energy. It's rolling friction, not static friction, that dissipates the energy like in the tires of a car. But let's not go off on a tangent about that. Anyhow, how fast is it going at the bottom? It's a conservation of energy question. Just like in number 1, E initial plus the work done equals E final, except there are no non-conservative forces, so therefore energy is conserved. There is no work done by friction because the question says so. In the beginning, there is no kinetic energy because it says the ball is released from rest. Now, there's a question in the homework that's a little different. It's almost the same problem, but the ball is rolling along and then comes to a ramp, so it's already got some kinetic energy at the top. You'd have to include some kinetic energy here in that homework problem, but in this one, I guess I don't need to bother with a subscript because H final is 0. I don't really need to distinguish between them. So at the top of the ramp, it has potential energy. As it goes down the ramp, that potential energy changes into kinetic energy. The center of the ball is moving from place to place, so you've got some translational energy, and the ball is rotating at the same time, so there's also the rotational energy. And we need some substitutions. This question gives us a grand total of 1 number, the 15 feet, or 15 meters for the original height. We also know the 9.8 we can stick in for G. And yeah, that's about it. We've got 2 numbers altogether. So what are we going to do about that? Well, I'm going to recopy that part of it. I'm going to recopy that part of it. Over here, for the moment of inertia. For a solid sphere, I equals 2/5 mass times the radius squared, the radius to the outside edge. And to reduce the number of different variables here, I want to substitute for omega in terms of V. So I equals 2/5 mr squared, because it's a sphere, a solid sphere to be precise. A thin spherical shell is 2/3 mr squared. From V equals R omega, we can get everything in terms of V. And then a very fortunate thing happens. Lots of stuff cancels out. There's an M in every term. So if I divide the equation through by M, I've got M over M there, M over M there, M over M there, and it's gone, which is a good thing because I didn't know M. Furthermore, the question didn't tell us the radius of the ball either. Not to worry. R squared divided by R squared, gone. So what we're left with is G times H equals 1/2 V squared plus 1/5 V squared, because these 2's cancel also. 1/2 of 2/5 is 1/5. Combining these two terms, you've got 5/10 plus 2/10 gives you 7/10. And yes, the question did give us enough numbers to solve for V. The center of the ball will be moving at 14.5 meters per second when it gets to the bottom. This is slower than if you greased up the ramp and, well, maybe a little more realistically, if you had some kind of a little wagon with nearly frictionless wheels on it, and you put the ball in that little wagon and let it go down the hill, it would get to the bottom faster than this, okay? The reason for the difference is if the ball rolls down, it starts with a certain amount of potential energy when it's at the top. If it rolls down, some of that potential energy goes into translational energy. Some of the potential energy goes into rotational energy. But if it just kind of slides down the hill, like if it's in a little wagon so that there is no rotation, then this term is 0. So in that case, all of the potential energy that you started with goes into translational energy. Whereas if it rolls down, only some of the energy goes into translational energy, and so it's not going to be moving as fast. okay? Or if you just like to say, you know, because the equation tells me so, if you have just purely translational motion, the kinetic energy would be 1/2 mv squared instead of 7/10 mv squared. You would have a 2 here instead of a 10/7. And actually, what you have right here depends on what's rolling down the ramp. If it had been a disc or a hoop or some other shape, they all have different coefficients in the formula for the moment of inertia. And here's where I'm going to set up something and show it to you. I'm just going to pause this for a moment. Okay. We are going to have a race. Solid cylinder, 1/2 mr squared, what amounts to a piece of pipe, or call it a thin cylindrical shell if you want to sound more like a mathematician. 1 times mr squared. Doesn't matter which one's heavier. Doesn't matter that there's a little bit of a difference in the radius. If you look back through the example I just went through, the mass drops out, the radius drops out. All that matters is that one is basically a very long hoop, and the other one is a very long disc, a cylinder, okay? A solid cylinder. So I'm going to release them on these ramps at the same time, and we're going to see who gets to the bottom first, who wins the ramp. Now, even without getting all mathematical and doing a calculation like the one that I just showed you, there's just simply the idea that inertia means sluggishness. If this one is 1 times mr squared, and this is 1/2 mr squared, this ought to be the one that behaves more sluggishly. So we'll see if that is actually how it works out. Put that one there. Put that one there. Hopefully I can manage to release these in a way where they don't hit anything on the way down. Here we go. Well, that went kind of fast, but actually on a video, you can kind of freeze it frame by frame if you want. It looked to me like the cylinder won the race, the solid cylinder. So now, for the finals. Solid sphere, 2/5 mr squared. Okay, there's a little bit less of a difference between 1/2 and 2/5, so this ought to be closer. But if I manage to not push anything one way or the other when I'm releasing them, the sphere should be the quickest one because it has the smallest moment of inertia. And again, it doesn't matter. It could be a bowling ball. It could be a marble. The mass and the radius drop out. So let's get all set up here again. Right up here at the top. No. Okay. Here we go. Well, that was awful close. I wasn't really looking at it from a good angle to judge which one got to the bottom first. Like I said, you can go back through the video and freeze the appropriate frame to see which one won. But if I didn't give anybody an advantage by giving a little bit of a push when I released it, it should have been the sphere that just edged out the other one. Okay, so where are we here? One more example, number 3. And then that's where we'll take the break between part 1 and part 2 because we'll be between topics. Ah, it focused. How nice. So this time we've got a disc rolling along a level floor, like somebody drops a quarter and it's rolling along the floor, okay? Well, except 0.8 of a kilogram would be an awfully heavy quarter. But aside from the numbers, that's sort of the thing that's going on. 4 meters per second, it tells you the friction force. How far will it go before it comes? This assumes it doesn't fall over before it comes to a complete stop. A quarter is pretty thin, but if the disc was a little thicker so it wouldn't fall over, how far will it go before stopping? So again, we'll do that with energy methods. I guess maybe over here is the place to go. Let's get all the substituting and canceling out of stuff out of the way right at the start. Just like in the previous question, the total kinetic energy is going to be the rotational energy plus the translational energy. And I'm going to make all the same substitutions that I used in number 2. This time we have a disk. So the rotational inertia is 1/2 mr squared. And just like before, I'm going to substitute from V equals R omega to eliminate omega from the equation so that everything is in terms of the same variable and I can simplify things. R squared divided by R squared cancels out. So the translational energy is this, the rotational energy is that. 1/2 plus 1/4 adds up to 3/4. Okay, so just as well to get that cleaned up right at the beginning, and then we can actually set up our conservation of, well, it won't be conservation of energy this time. This time the work term is not 0 because friction is present. There's work being done by friction. For the initial energy, the disk has some kinetic energy, 3/4 mv squared. For the work, well, we've done problems before that involved work done by friction. The work done by friction is always, well, I should write it out. In general, work done by any kind of force Work is the force times the distance times the cosine of the angle in between them. Friction always opposes motion. So if you're talking about work done by friction, the angle will always be 180 degrees. And the cosine of 180 is -1. So minus the force times the distance that the disc rolls. Final energy is 0 because it stops. It no longer has any kinetic energy because it's not moving, and it's on a level floor, so there isn't any potential. The initial and final potential energies are both 0 because it's just going across a level floor. So the kinetic energy it starts with gets, well, used up by friction, is putting it kind of crudely. More correctly, it's converted into heat. And then there just isn't any left. So I've got 3/4 mv squared equals force times the distance. And how far does it roll? It's asking for the displacement, S. Stick in the numbers. Mass is 0.8 of a kilogram. Initial velocity, 4 meters per second. Friction is 1.5 newtons. That's given in the question also. So 0.75 times 0.8 times 16 divided by 1.5 equals this thing's going to go 6.4 meters before it coasts to a stop. And speaking of stopping, this is where I'm going to put the break in the middle of section 9. When I return, we'll talk about angular momentum.